Can you hear me now? Okay, I think now the voice is good. Okay, perfect. So I was saying hello, hello everybody, hello people who watching me from all of the world. So first of all, I thank the Arab security team for giving this opportunity for the Arab security person passion. So we are missing just an event in the Arab community. We thank I thank also all the people that are watching now my talk, and of course, feel free if you have any question to ask me in the end of the session in the Hova application. So our talk today, we are going to discuss about the formal verification, but also how can we use this formal verification in the security of smart contract. So before talking about the topic or tackling the topic, I'm Souhail MSSASSI. I'm a research engineer now at QuantStamp. It's the top one in blockchain cybersecurity. I have been also a cybersecurity researcher more than 8 years. Was doing auditing, pen testing, and working in red and blue team. And also, I'm a blockchain developer, so I code smart contracts and also a blockchain consultant. So the agenda of today, we are going to talk a little bit about a general background of the topic. So we are going to discuss the blockchain technology, how it works, etc. The second aspect is problematic. So why we will use, for example, formal verification? What's the problem here, and how exactly we can tackle this problem? The third aspect is about software testing. And of course, some solution to our problematic is software testing, including unit testing. And we will view what are the problems of software testing, why we will migrate from software testing to formal verification. After that, we will discuss now about smart contracts and blockchain. So now we will have a little discussion about some technical things or technical aspects in blockchain and also in smart contracts. And of course, our main subject is about the verification of the correctness of our smart contracts, of course, using a formal verification. And the last thing is about conclusion and also some perspective in the security of smart contracts in general, and also how can formal verification help us to secure our smart contracts. So the first thing is, before discussing about formal verification, about smart contracts, we should understand the concept of blockchain technology. So there is a lot of definition to define blockchain. So there's some persons that define blockchain as a database, others as a protocol, as a technology, as a concept. So there's a lot of definition. But basically, blockchain is a term or a concept that have evolved from different concepts and technology. So if we look in the chronological order or a timeline of the evolution of the blockchain, of course, it began with cryptography. So cryptography is the science of ciphering a message or hiding a message using some cryptographical function. And of course, there is a lot of persons that contributed to this concept, including, for example, Alan Turing, the godfather of modern computer science. and he's the one who cracked the Enigma machine during the World War. So the science of cryptography has helped a lot in the evolution of blockchain. And of course, we all know 2009, Satoshi Nakamoto has published a paper and he presented Bitcoin. So of course, this Satoshi Nakamoto is, for now, it's an unknown person. But the idea it was the how can we, for example, ensure or make a financial system, but without any central entity. So now in the classical or finance, we are looking at two persons, for example, want to make some financial transaction, or for example, some legal entities, or they want to make some contracts. Of course, in this case, there is the concept of intermediate. So there is always a central entity that will ensure that everything is working well. If, for example, the two parties are respecting the terms of the contract, etc. But Satoshi has thought, why can we do the same system but in a decentralized way without any central entity? And in addition of that, we can ensure that each entity has respected the what we agreed on, and everything is correct. And of course, to do this, Satoshi has published a paper, a very interesting paper, discussing about some technology and some concepts. And included in this concept, he talked about a consensus called proof of work. So proof of work, it's a consensus that each node in the blockchain agree. And of course, the way how proof of work works is about calculating some hash. And if you find this number or this hash, you have the right to verify the block. And of course, you are rewarded by Bitcoin. This is another subject about mining, about how Bitcoin work, about consensus. But it's very important to understand how blockchain works and what is the evolution of blockchain. After that, of course, we have a rise in cryptocurrencies, more technologies, more blockchains, etc. And a person named Vitalik had the idea that, okay, Bitcoin is the revolution or the next revolution. Why can we think about a program decentralized instead of just decentralizing the financial transaction? And of course, he created with his team Ethereum, and also the concept of smart contracts, when he will focus on decentralizing or giving the power of decentralization to the developers. So in a nutshell, that's a blockchain. And of course, there is a lot of technical details that we will discuss more later. So now the problematic, of course, our subject is formal verification, and in each technical revolution, or when we want, for example, to invent a solution, you must have a problem or a problematic. And here what we are looking, it's rockets. It's called the Ariane 5, and in this rocket, to explain to you, it has a program, or it's like a central program, a master server, and this master server, he control all the rocket. And of course, just after 3 minutes of launching this rocket has exploded, and million of dollars has been wasted. So of course, scientists and the team thinks why this problem has occurred, and of course after some deep analysis they find that it was what we called an integer overflow. So an integer overflow basically it's a memory problem in the size of an integer. So when we want to store, for example, an integer in memory, we have a fixed size, we have a fixed size. But if we pass or give a value that exceed the maximum value, we will have a problem, and of course this value will be changed to zero, and it will be resetted, and of course it can cause a lot of damage and a lot of problems, and it's very difficult to detect this kind of issues. So just with a little problem, one line, we waste $1 billion. So of course now you are going to ask me, so how can we fix this kind of problem? Are we going to do a code review line by line, or are we going to, for example, do some audits, external audits, etc.? So of course it's very difficult, even with internal or external audits, and also with some code review. Of course a human cannot read millions of line code, and even if they can read this, a human can make mistakes. So of course we need some technical methods that will help us, first of all, to find these bugs, find these mistakes, and second of all, to automate this process. So now we are talking about software engineer. So in software engineer, there is a lot of concepts that can help us to verify the correctness of the code. So when I say the correctness of the code, I'm not talking about the, the security part or the functional part, but I'm talking that this program that we created, it should behave like or the same way that we expect it to behave. Of course, this is just a first scenario. There is also another scenario, and now this scenario is in the blockchain case, and it's called the DAO hack. So this 4 lines of code has caused more damage to a lot of damage to the Ethereum community and to a lot of smart contracts. So here, of course, it's a simple contract. We will discuss more about this problem or this bug in this smart contract. Of course, here it touches the security part, but what we should know is that this DAO hack has caused the fork of Ethereum. So we now have the Ethereum Classic and Ethereum, and it causes a lot of smart contract to be stole some ether from hackers. So now we understand the problematic. The problematic is that we have a code, and inside this code it can have some bugs or some vulnerabilities. And of course, in a simple contract or in a simple program, yes, maybe we can do some white box testing and view if there is any bug or vulnerabilities. But in some longer programs or bigger programs, and also there is some weird inputs that can do abnormal activities. So here classical reviewing or classical testing won't work. So of course, what are the methods that exist in the software testing world. So when we are talking about software testing, we have two different types. We have the functional testing and we have the non-functional testing. So functional testing, we can find unit testing, integration testing, system testing, acceptance testing, and in non-functional testing, we can find, for example, performance testing, security testing, usability testing, and compatibility testing. So non-functional testing, it's some tests that will focus not on the functional part, but on the non-functional part. What do I mean by this? So for example, performance testing, it's not something related to the logic of the program or the logic of the code. So we are just going to test the performance of the code or the performance of this machine or service by using some stress testing or some other, or sending millions of requests per second, etc. We have also security testing. For example, pen testing. It's a regular security testing that we will focus just on the security part of the code. Is this code, for example, can lead us to some attacks, to some remote code execution, etc. And in the functional testing, we can have the unit testing part that will test some parts of our code, some functions, etc. So just to clarify a little bit about unit testing, so imagine that we have this code. So it's a simple code written in Python, and we can apply the concept of unit testing here. So imagine here we have this function. This function is called max, and it takes as an argument two input, or two numbers, x and y. And in the first line, we are making a regular comparison. So if x is equal to 5.41, we are going to return y. But if x is greater than y, it will return x, else that it will return y. So I know that it's a weird max function. The normal one, it will be if x greater than y, it will return x, else return y. So but I did this script or this code intentionally just to give you an idea about unit testing. So in this function, imagine, for example, we don't have the code of this function. For example, it's a black box testing. Or for example, we have the code, but it's not obvious that, for example, we are comparing, we have a specific case. So unit testing, basically, we have different scenarios, and in these different scenarios, we have also expected behavior or expected output. So we have some inputs, and with these inputs, we have also expected outputs. So for example, max 5, 3, it's 5. So it's very logical. So 5 is greater than 3. So the function max should return to us 5. For example, other example, max 10 with 2.3. So of course, here in this scenario, the program should return to us 10. So unit testing will make some scenarios with, of course, the expected behavior, and we are going to run a program that will test this different scenario and verify if it matches the expected behavior. Of course, in this case, for example, if we make any number other than 5.41, it will correct in a normal way. But imagine, for example, in this code, imagine, for example, if we put x is equal to 5.41, and in y we make 2. So the first line of comparison, it will verify that is verified. So x is equal to 5.41. 1, but it will return to us 1. And of course, it's not the expected behavior. 5.41 is greater than 1, so the max function should return to us 5.41. So of course, to detect this weird behavior in unit testing, we should include this scenario. And it's very difficult. Of course, in this script or in this program, it's very obvious, but in more than 90% of the code, or in the majority of the projects, it's very difficult to look for weird activities or weird inputs that will trigger different or abnormal activities. So of course, we cannot test all the possible scenarios. So for example, in the max function, there is an infinite scenarios, and of course, it's very hard to test all these scenarios. So our goal, of course, in unit testing is to minimize this number of scenarios, but at the same time, we should verify the correctness of the code. So here it's just doing, for example, some unit testing. So there is a lot of tools or programs that can help us to create some scenarios and also to run some tests. We can find them in the classical application, but also in the GApp or in the smart contract context. So we are just here verifying that the exact the matching inputs match the correct behavior. So, but in another hand, when, for example, we verify with 5.41, we will find that there is some abnormal activities, and it's very hard, as I mentioned, to look into this weird behavior. So of course, this is some limitation of unit testing. So now scientists and mathematicians think about some solution to this limitation of unit testing, and they created this concept of formal verification. So formal verification or formal methods are techniques or are some mathematical techniques based on what we called the spec or the specification, and we are using this concept to test the correctness of a program, of a smart contract, of an embedded system, etc. So of course, in this case, we should understand how exactly formal verification work. So here we have a system. We have a system, and inside this system, it can be a web application, it can be an embedded system, it can be a program, etc. To verify the correctness of the system using mathematics, we should do what we call modeling. So of course, to prove something in math, we have mathematical expression, we have conditions, we have proofs, we have a lot of concepts that we use in mathematics. And of course, in the other hand, a system, it can be a web application, it can be a circuit, it can vary. So this is two different things. So to prove a system using math, this system, it should understand exactly, or we should express it by mathematics, by mathematical expression or mathematical function. And this process is what we are calling modeling. So the modeling of a system, it consists of taking a system or taking a program, taking a function, and convert it to mathematical expression that any mathematician can comprehend. And of course, this process is very difficult. So it's not easy to do this process, and it takes also some time, and also it needs some knowledge. So you should recruit mathematicians, you should recruit persons specialized in formal verification, etc. After, of course, modeling the system, we have what we call the system model. So now in the first part is the model system. Now, of course, uh, we should prove the correctness of this program. But the computer don't understand what is correct. So to evaluate the correctness of a program, we should have a reference. What is correct? The computer don't know or don't understand the concept of correctness. He should be based or should have a reference on how exactly this program works. And to do this, we should have some specification or some spec. Of course, uh, we have some requirements. So this requirement, it can be a written requirement, and of course it will explain to the security guys or the one who will do the formal verification how exactly this program should work and how exactly it should behave. And of course these requirements are written in a classical or in standard language. So of course we should do the same thing that we do with system. We should do some modeling, but here in our case, in the requirement parts, we don't talk about modeling, but we talk about formalizing. So make our requirements formal. And of course after this process, we now can call or discuss about the spec or the specification. So now we have a specification. So the spec is rigorous or a mathematical expression that explain to us the requirements of the code. And also we have the system model and its expression or modeling of the system in a mathematical way. So now we can do what we call the proving or the model checking, for example. So model checking or proving, it will verify if the system model, it matches our spec in a mathematical way, of course. And of course, if they matches this, or if this kind of spec is satisfied, so we can say that yes, we are guaranteed that our model system it matches the spec. But of course, if it's not, we should have a counter example. So here we we have a counter example, and with this counter example, we can help the developers understand more how exactly this bug is triggered and exactly how also they can fix it. And of course, after fixing the bug or fixing the problem, it's an iteration process. So we will also make another test and verify if we implemented uh, the fixes or the remediations in a correct way. So of course, this is a hierarchy or an overview about formal verification. Now, uh, of course, formal verification it's not cheap, so it costs a lot and it takes a long time to do it. So of course, we should understand where exactly, what time exactly we should do it, and how also we should do it. So of course, there is a lot of scenarios, and each scenarios have some impacts. And these impacts or this risk, it depends on two attributes. So this risk, it depends on the impacts and also the probability. So of course, the fusion or the union of these two attributes will help us to understand more what method exactly we should do. Should we, for example, do formal verification, or we should do, for example, just classical testing or unit testing? So if, for example, we have a risk associated and this risk is harmless, and the probability is likely. So unit testing is very sufficient here. And also, even for example, we have a risk that is harmless and it's very rare. So to be honest, it's not very important to go deeper and do some unit testing. But what we are afraid is from the impact that's going to be catastrophic. For example, the explosion of a rocket. For example, a smart contract that we can steal from it millions of dollars, etc. So if we have, or if the probability of this risk is very likely, we can use unit testing in addition with formal verification. So if the probability is very likely, it's more than 70% that just unit testing will trigger or will detect this weird behavior. But the problem here is, imagine for example, we have a risk, a catastrophic or high critical risk, and the probability is very rare. So it's very weird, for example, inputs or very weird scenarios, and this weird scenario will lead to us, for example, to a critical impact. So here in that case, we can of course use formal verification. So when we are going to use formal verification is in the, if the, for example, the impact is catastrophic and the probability is very rare. Of course, you are free. You can do a formal verification anytime you want, but you should be aware that formal verification will takes time to verify to do it. Of course, writing spec and modeling the system, it's not something that is very easy to do. And of course, you should have some human resources to have the knowledge of formal verification. And also, of course, formal verification, it's in the research and development part. So be aware that it will cost you a lot of money. So now we understand where exactly we can use formal verification. Now, what are the different stages in formal verification? So of course there is different integrity level and different stages and different methods to do formal verification. And it depends. So there is a lot of different scenarios, and it depends on each scenarios, depending on the cost and also the risk. So of course, the first thing is to do formal spec. We already talk about what is specification, the cost and the risk of formal spec. It's very low if we compare it to other stages, but when we are talking about formal proof, the risk is very high, and it's very difficult to implement them. Same thing with model checking and also abstraction. So model checking, and we are still here in the integrity level 2, we have the cost high, but the risk is very low. But when we are talking about abstraction, we have the cost that is high and also the risk is very high. So of course, these different stages of formal methods will help us to gain more confidence on our smart contracts or on our program. And just to give you an idea about some techniques, for example, here we have what we call model checking. So here we have a classical code that contains 3 lines. So the first line, it will compare x with 0, and if x is equal to 0, we are going to set it to 1. The second verification is y less than 2. If it's this, we are going to increment y by 1. And the Second, also, or the final verification, it's a classical verification, and after this we will do a block or a set of instruction. So model checking consists to draw a tree of all the different combination or all the different scenarios that it can be. So here what you are seeing, it's a tree that it will represent all of the different states of our program. So with or using this tree, it will help us to understand more the logic of our code, and also using model checking, it will traverse all the different paths. And if, for example, there is a weird behavior or abnormal activities, in this case, model checking will verify this scenario. But of course, there is some limitation. Not all the programs that we have we can draw a tree, a finite tree. So it works only with what we call FSM, finite state machine. Of course, there is some codes that we cannot represent by this tree, and it's very difficult to verify the correctness using the model checking. So now we understand a little bit about formal verification, what are the different stages, what is a formal spec, and also how we can use it. Now we are going to talk about how can we use formal verification in the concept or in the blockchain, and specifically in the context of smart contracts. So we already talked about blockchain, but just to give you another idea. So here we have a network blockchain. So a network blockchain is composed from nodes. So this node or this machine will execute our code in a decentralized way, and they are responsible for verifying that everything is correct. And of course, if everything is valid, everything is correct, they will store this information on the ledger. So a ledger is like a big database, and it will contain all of different transactions and all of different blocks. So in each block we have different transaction, and in each transaction it's represented by its nonce, a timestamp, etc. So of course, in the blockchain architecture we have different layers. So here it's like the OZ model. So the first layer, it's the infrastructure layer, and it's composed from nodes, storage. Of course, there is a communication between these nodes, so we should have some kind of network. And after this layer, we have the platform layer. Of course, we can find some APCs that will provide to us some APIs or some WebSocket connection to communicate directly from the outside to the blockchain. And also we can find some algorithmic or some concepts in the distributed computing layer. So now we can talk about consensus, transaction, what are the mechanisms used in security to secure the blockchain, like hashing, encryption, etc. And in the final layer, it's the application layer. And now we can find, for example, GApps, smart contracts, etc. So all of this layer, of course, to secure the blockchain, we should focus in these different layers. But now, in our case, we are just talking about software and the application layer, so we want to just focus on the smart contract part. But of course, it doesn't mean that we should not verify also the other layers or the security of these other layers. So, as I mentioned, the part that we will focus on is about the smart contract. And of course, smart contracts, it's programs like the classical program. So it's a set of instructions And inside this set of instruction, we will verify, of course, or we should verify the correctness of this program. So in the case of smart contracts in Ethereum, there are programs that are written in language that we call Solidity. So it's a language that is based on ECMAScript. So it's like JavaScript in a way. And of course, there is the concept of unit testing in a smart contract. So a smart contract, basically, as I mentioned, it's a program. And in this example, or in this scenario, for example, we have John and Bob. And Bob, for example, he wants to sell his house using the smart contract. And John, also, on the other hand, he wants to buy a house. So the smart contract, it will act like an intermediate, and it will verify that everything is correct and everything is okay in an autonomous way, and of course in a transparent way. So the smart contract, it will receive the assets, and it will distribute this assets. So instead, for example, of the classical things and waste times and waste also money on intermediate, the smart contract will help us, of course, to handle this logic. So just to give you an idea about how smart contract is written, so here we have a classical smart contract. It's a hello world, and here we have the definition of a contract called hello world, and inside of the contract we have different methods or different functions. And here we have the function called get. So it's a public function, and it will return to us a hello message, so hello contracts. So this is the language that is called Solidity, and of course the extension is Sol, and we can begin coding with Solidity using Remix IDE. It's an online IDE that will help us, of course, we developers, to code the logic of our smart contract, but also help us to deploy this smart contract either in the main network or in test network. Of course, when we are talking about code or about programs, we have major problems in the security parts. And now we can talk about vulnerabilities in smart contracts. So I already did a lot of talks talking about vulnerabilities in smart contracts. Our topic is not exactly what are the different vulnerabilities in smart contracts, but our topic is to detect these vulnerabilities using formal verification. So of course, in the smart contract part, we have different layer or different entities that we can find vulnerabilities. So we have three layer or three source. So the first layer is the EVM, or the Ethereum virtual machine. It's the machine that will execute our code. It's like the JVM, the Java virtual machine, in the case of Java. The second thing is about the blockchain. So the architecture of blockchain and how it works and different protocols or consensus that used in this blockchain. And the third thing is about Solidity code. So inside the code, we can find some vulnerabilities. For example, Reintroduce Attack, some casting, some overflow, etc. So back to the DAO hack, or what we call the Reintroduce Attack. So it's a very classical vulnerability that caused a lot of smart contracts, and also it's a very weird behavior. So at this time, it was very abnormal. So here we have two contracts: the DAO contract, and we have the attacker contract. So here the objective of the attacker is to access another time to the contract and trigger this function withdraw, but without getting to this last line of code, because in this last line we are subtracting the balance. So imagine that we will execute just this first line. So the call value, it's the function that will send to the attacker the ether. So basically that was the concept, and hackers succeed to do this kind of manipulation. We have also another vulnerability, and it's very classical. It's transaction ordering dependency. So it has something related to how blockchain or Ethereum works. And of course, in Ethereum, miners have this power to order their transaction or also change on the timestamp up to 900 seconds. So of course, here we have a classical smart contract, a marketplace, and we have a seller and a buyer. So the seller, for example, in the first time on the first call execution, it will call the create offer. So for example, it will sell 10 tokens for 1 Ether. So the buyer is very happy with this offer, for example, and he will accept this offer. After that, the seller will update his offer to sell 1 token for 1 Ether. So if, for example, the miner or the order of this transaction is create offer, accept offer, and update offer, it won't be a problem. But imagine that, for example, the order is switched and we have a create offer and update offer, and the last thing is the accept offer. So here we will have a problem because the buyer will accept the last offer and it's selling 1 token for 1 Ether. So it's a very hard problem to tackle, and there is of course a different solution to solve this problem. But to detect this problem using classical or standard unit testing or manual reviewing the code, it's very difficult. So now, how can we use formal verification in our case or in the smart contracts case? So, of course, there is a lot of tools and that can help us to do formal verification in the case of smart contract written by Solidity. And one of these tools is called Solk Verify. So Solk Verify, it's a tool that uses some boogie logic, and of course they verify using they do some verification using the Z3 and CVC4 algorithm. And inside the smart contract or in the Solidity contract, we have the spec in it's like a commentary or an annotation, and inside this annotation we declare exactly what is the correct behavior of this code. And using the boogie verifier, uh, Solk Verify will verify exactly the correctness of our smart contract. And of course, after that, you can be sure that this smart contract is behaving in a normal way or in a correct way. And of course, after this, it will return to us the verification result, and if everything correct, it will output us that everything is okay. But if it's not the case, it will automatically tell us that there is a problem in this code. So here it's classical contracts. So if you view here in this example, we have this kind of annotation that we talked about, and it's a kind of a spec. So here we define some invariants, and of course here we are defining that x, it should be equal to y in the first constructor or in the first deployment of the contract. But after that, for example, in this function, we do some other annotation. So we have some precondition and post-condition. So precondition, it's a condition that we should verify before executing the function call. And post-condition is a function that we verify after executing the function call. And we have, of course, a classical function. It's called add to x, and it takes as an integer n. And they just do a simple verification, or x it's equal to x plus n. So of course here automatically it will verify using the annotation that x, it should be equal to y plus n. Of course, if, for example, here and here using formal verification, we can find, of course, some problems, because here, of course, we are using a classical addition, not using some libraries to do the addition, and of course, it can trigger what we call an overflow attack. So yes, it at the first sight it seems very logical that x is equal x plus n, but of course we have some weird behavior, like for example the overflow. Here it's the same thing, so we just verify that y is less than x, and of course after the execution of our program, here we have the output. So for example, we have the constructor that is working well, the transfer function working well, the self-destruct working well, etc. But in the other hand, if for example we have a problem, so here the self verify will return to us an error, and it will output to us exactly what's the line of the error and how exactly what are the inputs that are responsible for such weird behavior. So of course there is a lot of tools that we use to verify the correctness of our smart contracts, but Sock Verify is a tool that is very powerful, and it can help us to verify the security and also the correctness of our smart contracts. So now what are the conclusion and the perspective of the formal verification? So for now, we don't have any kind of concept of universal verification of smart contracts. So it's very difficult to find a tool that will verify the correctness from A to Z of the contracts. And also, we don't have a full modeling of the EVM machine. So it's also very difficult. But in conclusion, smart contracts are very critical programs, and of course we should verify the correctness and also verify the security part. Also, to verify this, we have different techniques and different methods. So we have the manual methods, so code review, for example, looking line by line to find different problems or different bugs. We have also some automated techniques like unit testing, but as we already seen, unit testing have some kind of limitation. So we cannot apply this kind of concept for example, some critical programs or critical smart contracts. And we have the last thing, it's the formal verification. So formal verification, of course, it's way better than unit testing and classical testing, but also it costs us some money and also some time to do this. And of course, it will just verify if our code or our program, it matches our spec. So if, for example, the spec is incorrect, automatically we will not verify in a correct way the correctness of our smart contract. So this is the end of it was the end of my talk. I hope that you learn something in the concept of formal verification in blockchain, in smart contracts. So if you have any question, feel free, of course, to ask me on the Hova application. So I will look if there is any question. So I'm waiting. If you have, of course, any question concern the blockchain part, the smart contracts part, and also why not formal verification, our main topic.